Here is an order priced at $100.0525. It is positive, it is well-formed, it sits calmly between two perfectly ordinary prices. And the venue rejects it, not because the price is unreasonable, but because the grid for this instrument steps in whole cents, and this price lands a quarter of a cent above a step. Decimal precision is not a display concern. It is a gate. In this tutorial, we build that gate so it answers exactly, with no floating point ambiguity, and tells the sender the two valid prices on either side. For things. First, an input contract where every price is an integer count of atoms, so the question has one exact answer. Second, the test itself, which is a single integer modulo against the effective tick. Third, the rejection payload. Not just a no, but the remainder, both neighboring valid prices and the distance to each. Fourth, the part most implementations skip, the identity of the policy that produced the decision, so the same call could be reproduced months later during an audit. The complete article, both reference implementations and an interactive playground are on the fintechbuilder.com, linked in the description. The validator takes exactly 4 inputs. The price, as a positive integer number of atoms. The effective tick size, also in atoms. The price scale, which says how many atoms make one currency unit. And the identifier of the policy that supplied that tick. In our canonical fixture, the price is 1,500,000 atoms. The tick is 100 atoms, and the scale is 10,000. Divide by the scale, and you get $100.05 on a 1-cent grid. Notice what is absent. The validator never infers the tick from the price. Resolution happens upstream in a point-in-time reference service. Why carry prices as integers at all? Because 100.05 cannot be written exactly in binary floating point. Neither can 1 cent. Ask a floating point remainder whether one lands on the other, and you get a value that is almost 0, but not 0. And now your accept or reject decision depends on a tolerance somebody chose. Integers remove the question. 1,500,000 atoms divided by 100 atoms is 10,005. Remainder exactly 0. There is no epsilon, no tolerance, and no rounding mode. A tick grid is a ruler, and integer atoms let you ask whether the price landed on a mark. The rule is one line. A price is valid when price atoms modulo tick atoms equals 0. 3 symbols carry it. P, the submitted price in atoms, always positive. Tau, the effective tick in atoms, resolved before validation ever runs. And art, the remainder in the same atoms. That is the entire mathematical content of this control. Everything else in the implementation exists to make the decision reproducible. Validating the units, retaining the policy identity, and computing what to tell the sender when the answer is no. The arithmetic is trivial. The contract around it is the actual work. Run the canonical fixture. 1,500,000 atoms divided by a 100-atom tick. The quotient is 10,005, and the remainder is 0. The price is valid, the state is accepted, the reason is on grid. Now, look at the neighbors. Because the price already sits on a mark, the lower valid price and the upper valid price are both the price itself, and both distances are 0. That symmetry is the signature of an exact hit. An accepted decision still carries its policy identifier, its scale, and its remainder because an operator reading the record later needs to see what was checked, not just that something passed. Now, I'll move 25 atoms. Keep the policy, keep the tick, and submit 1,525,000 atoms instead. In display terms, that is $100.0525, a quarter of a cent above the grid. Visually, it is almost nothing. Arithmetically, it is decisive. The remainder changes from 0 to 25, so the state changes from accepted to rejected, and the reason becomes off-grid. This is the whole lesson of the topic in one substitution. Visual proximity to a valid price is not grid membership. and a price that rounds nicely on a screen can still be unrepresentable on the venue's ruler. A bare rejection is a poor answer. It tells the sender something is wrong without telling them what would be right. So the rejection carries both neighbors. For our off-grid price, the lower valid price is 1,500,000 atoms, and the upper is 1,600,000, 25 atoms below and 75 atoms above. The sender can now round down, round up, or escalate, using values the venue already agreed are legal. And the invariant is worth stating. The submitted price always lies between its reported neighbors, and when it lies exactly on one, both collapse to the price itself. Here is where teams get hurt. The tick is not a property of the instrument forever. It is a property of a policy that was effective at a point in time. Under a 100-atom policy, the grid steps in cents. Under 50 atoms, it steps in half cents. Under 25, quarter cents. Under 500, 5-cent increments. The same submitted price can be perfectly valid under one policy and rejected under another, and neither answer is a bug. That is why the policy identifier travels with the decision. Without it, you can reproduce the arithmetic, but you cannot reproduce the ruling, and an audit needs the ruling. Now the evidence boundary, because this is a regulated area and precision about claims matters as much as precision about prices. The source fact is that Securities and Exchange Commission Rule 612 governs minimum pricing increments for covered national market system stock quotations and orders, and that the 2024 amended half-cent regime for certain stocks is under temporary relief until the first business day of November 2027. That is what the source says. It does not resolve the tick for our synthetic instrument or for any other product, venue, jurisdiction, or effective date. Every price, policy identifier, and grid in this tutorial is repository-authored synthetic teaching data, and this package deliberately does not activate the delayed regime early. It is equally important to name what sits outside the fence. This is the explicit resolved tick variant. The caller supplies the effective tick, and the validator applies exact divisibility. It is deterministic, and it is cheap, and it does not resolve the tick. Regulatory tick assignment, which derives an increment from rule-specific market statistics, is a materially different algorithm and belongs in a reference data service. Venue product tables with price bands and per-product increments are a third thing again, common in derivatives and options, and not universal. Choosing the wrong one of these three is not a tuning problem. It is the wrong algorithm. The code follows that order exactly. Validate first. Price, tick, and scale must be positive integers. The policy identifier must be a non-empty string, and a tick larger than the price is refused outright. Then one call to integer division gives the quotient and the remainder together. The lower neighbor is the quotient times the tick. The upper is the same value when the remainder is 0, and one tick higher when it is not. Finally, return a structured result. Validity, remainder, both neighbors, both distances, the reason, the state, and the policy context. 3 branches, and every one of them is explicit. The package does not stop at one worked example. 7 named scenarios each sweep 61 deterministic parameter states, and every state is recomputed from the reference function. The canonical sweep walks a price across a 1-cent grid and lands 13 accepts against 48 rejects, which is exactly what a fine grid and a coarse step should produce. A coarse 5-cent policy rejects 1,015,025 with a 25-atom remainder and neighbors 500 atoms apart. A quarter-cent policy accepts 1,750,000. These are not backtests. They are controlled counterexamples, where one driver moves and the rest of the contract stays fixed. Be precise about what a pass means. It means this price is on this grid under this policy. It does not mean the order passes every other venue, broker, regulatory, credit, position, or market access check. It does not certify exchange conformance, legal compliance, production latency, operational resilience, or the safety of an override. And when a result surprises you, debug in order. Confirm instrument, venue, session, order type, side, and policy identity first. Then confirm the integer scale, the units, and the as of time. Then confirm the equality rule and the remembered state. Recalculate the invariant before you change any code, because most surprising outputs are correct answers to a different question. So, prices as integer atoms, a tick resolved upstream by a point-in-time policy. One modulo to decide. Both neighbors returned when the answer is no, and the policy identity retained so the ruling can be reproduced. That is a price grid gate you can defend in an audit. Carry the result forward only with its scope, its clock, its state, and its evidence label. The complete article, the Python and TypeScript references, the frozen fixtures, and the interactive playground are on the fintechbuilder.com. Link below. Continue next with price band validation, where the question moves from whether a price is representable to whether it is permitted. Continue the learning path at the fintechbuilder.com, where the full order control articles, source code, visuals, and playgrounds carry this gate into price band validation.